All right, good afternoon.
Good afternoon.
Hello.
How is everyone today?
Pretty good.
Cool.
It's a Monday.
It's the Monday. It's the first Monday of the year.
I have a bit of a question. I don't know if you would have an answer to this.
Okay.
I know that in some schools online classes cost more than physical classes. Is that the same as Pep Clark?
I don't believe there's a difference in price,
Okay.
but you should be able to check that in enrollment.
There is. There's a bunch of online course fees.
Are there really?
It used to be like $30, now it's like 60 or 70.
Isn't it? No, dang. I thought it was like 25, but
It was $30 for like the, I don't know, accessibility fee or whatnot, but yeah, I got like a ton of them this course.
Huh.
oh dang.
Interesting.
Yeah,
Well,
I know that.
These don't count as, these are in person, then we shouldn't get charged for it.
Yeah, this is an in-person class, so.
Yeah, I know that WSUB was like that. You would pay more for in-person classes and pay less for online classes. And when COVID hit, when people started complaining about all their classes, the prices not adjusting, they just extended the amount of time that the classes went for, so lowering prices.
Huh. Interesting. Okay, yeah, so I'm obviously not aware of any of the costs, but CTC Link should show you your bills. But yeah, so this is an in-person course, and it's just kind of because of where things have been over the past few weeks and where I think they're going this week, that I decided our first week we're going to do this as a remote. But that's not a change in the modality of the course long term, and our tentative plan is that Monday we will be back to being in person, and we'll be in the STEM building, SBG room 155. But whether in person or remote, it's always going to be Monday, Wednesday, 1 o'clock to 3:10. All right. Any other questions up front? All right. Well, so this is CSE215. This is a discrete structures course, and as I tell people during advising, discrete structures is kind of like the theory, the math, the logic, some of the mechanics behind computer science, behind a lot of the stuff that we do. We write programs and we wonder, are these programs correct? And we have things that we do to assess whether our programs are correct or not. There's discrete structures underneath that sort of process. And so this is a course that touches on a number of subjects. There's a fair amount of mathematics, there's logic, there's computer science, and there's lots of weird stuff. There's lots of things that will come up about sort of the nature of thought or the nature of existence or reality, paradoxes, things like that. So we cover a bunch of different topics, but they all in some way or another relate to what we're doing, as computer scientists. And in particular, a lot of what we do in this course relates to CSE222, which if you're a CS major, you're probably taking CSE222 this quarter. And so there's a lot of interplay between this course and that course. So let me start.
I'm thinking if this quarter is that a problem.
So,
I wasn't able to.
You weren't able to take what?
22. I'm only taking 215 and math at that too this quarter.
It's only a problem if you're planning to transfer this coming fall to a university. If you're going to do Clark next year, you can take 222 next winter instead.
Wait, what's the problem? If will we not be able to go to WSUB in the fall?
Yeah, CSE 222 is required to transfer as a junior.
Oh, right, okay. Yeah, so that's what we take. Oh, yeah, so that's...
right? But if you wanted to take it this quarter and you're running into a schedule problem or something, talk to me about it like right away. Like send me an email in the next few hours, and let's see if we can figure out a way to make that work. All right, so Canvas details, right? So again, this is an in-person class, but for this first week, we're meeting remotely. So you already know the Zoom info because you're here. And if you don't, then you can find it on that Canvas page. So I'm turning off everybody's microphone, and if you want to talk to me, go ahead and turn your microphone on, and feel free to use your voice, and then just stay muted when you're not talking, and that'll help keep down background noise. All right, so when we get back to in person, we're going to be dealing with COVID safety. So there's a PDF on Canvas that you're required to go through and read and take the test at the end of, to make sure that you've familiarized yourself with the various procedures for being in person in the middle of a pandemic. So this is, there's probably no surprises in here, nothing that you haven't already seen or read or heard. There's a great picture, by the way, for why we wear masks. And then there's a test at the end, and you're required to take the test, but I'm not required to collect the answers you turn in or give you a score or anything like that. I don't know why. It's just the way they made the rules. But there's 10 questions at the end here that you should go through on your own just to double check your understanding of the material. And this should be in the syllabus for every course that's in person, so I think you only have to go through this once. But make sure you've looked through that, and if you have any questions, talk to me or follow the resources listed in the PDF. All right, so let's go through the syllabus, and I'm going to use my own copy of this instead of reading it through Canvas. So, course information, topics, prerequisites, all that stuff, you can read all that. It's stuff we've already mentioned. The textbook for the course is an open access textbook, so you can download it as a PDF through the syllabus. It's a good textbook. It's well written. I've been using it since the second year I taught this course. And I will be giving homework assignments from this text, so you definitely want to download it and keep it as a PDF. I don't recommend printing it out because it's big. There's topics in the text that we will not go over. There's some topics we'll go over that are not in the text. And so there's a link to an additional textbook that we'll use for some of the units we talk about. Other textbooks that might be useful, so I'm on the wrong syllabus. All right. Same deal. All right, so you've got my email. There's no Z at the end. My office hours are going to be strictly online, even though this is going to be an in-person class. I'm sticking to Zoom for office hours. So you can always go to engrcs.com schedule to see my hours. And right now those are set for Tuesday and Thursday mornings, 8 to 10, and Friday morning, 9 to 10. So, but always check there if there's any question about my hours, and if I make changes, I'll post them on that site. So there's a textbook link. Everything I just said applies to that. I'll let you read the course outcomes, but these are the things that you're supposed to come out of the course understanding, and when you transfer to a university and they give you credit for discrete structures, these are the things they're expecting you to have learned. Tentative schedule will modulate away from this pretty quickly. We're going to start with set theory. That's going to be what we talk about this week, followed by logic, number theory, proofs, induction, counting, and so on. We'll definitely go through all of these things, and we'll go through algorithms and language and automata. We'll do a lot of Boolean algebra. We may or may not get to graphs and trees. We'll see how much we get through that. And the lineup of these courses with these weeks will shift around over time. But that's a good starting idea for what we're going to cover. So grading, you're going to get a lot of homework. Every week you'll have a homework assignment. That'll be worth 25% of your grade. I strongly recommend taking the homework very seriously. Right? The homework is the main way you're going to learn these concepts, and your exams are going to look an awful lot like the homework questions. They're just going to be different questions, but they'll be the same kinds of questions. So if you can do the homework, you can do the exams. And if you can't do the homeworks, you're going to have a hard time on the exams. So you sort of have the entire quarter to practice doing, the midterm and the final exam. And midterm and final together is 65% of your grade. So do the homeworks as if you were doing the exam, which means, take notes during the course, reduce your notes to note sheets, and try to use those note sheets to do the homework. Right? Try to resist the urge to go online to look at Stack Overflow, certainly look at Chegg or places like that. Use what we've talked about in class and what's in the text to try to understand how to do the homework. And if you're having troubles, come and talk to me, right? I've got office hours 3 days a week. You can talk to me during office hours, or you can ask questions in class. Usually in the beginning of class, I'll say, are there any questions? And that's a perfect time to ask about homework. Like, I really have no idea how to start question 8. Or, I got this question this far, but I don't know what to do after that. Those are great questions to ask in class. And guaranteed, if you're stuck on something, other people are stuck on it also. And maybe you're stuck on something that I completely forgot to talk about. And maybe all 25 people in the class are confused about this, right? If one person will ask about that in class, we can have a conversation and resolve all of that, confusion. So class time is a really good chance to ask about homework questions. The worst place to ask is email. Emails I will generally deal with once a day, and I won't do a lot of back and forth. So if you have a question like, what day is the exam, or, how many pages of notes can we use for the midterm, or something like that, you can ask me a question, I'll give you an answer. We're not going to get into a lot of back and forth, right? Where we end up swapping, 20, 30 emails in the course of a conversation. If we want to have a conversation, come to office hours or ask in class. Okay? So homework is 25%, midterm is 30, final exam is 35. There'll be one programming assignment, 10%. And that's not intended to be a big deal. It's just a way to sort of get some hands-on perspective on some of the things we'll be talking about in the number theory unit. So that'll be the other 10%. A lot of the rest of this you've probably seen in every other syllabi that you've looked at for your courses at Clark, so I'm not going to go through this in a lot of detail, but there are numerous support services available for students at Clark, including the Disability Support Services Office, DSS. If you feel like your ability to perform in your classes would improve by having some kind of accommodation, for example, when we're in person, if you need to sit in the front row to be able to see the board, or you need to be able to sit in the back row so that you have a wall behind you, or you come to class late and you need some kind of accommodation around that, or you need extended testing time, talk to the DSS office or talk to me and I can direct you to that office. There are all kinds of accommodations that can be set up. You can have note-taking services. You can have flexible deadlines. There's all kinds of things that can be done. And DSS will work with you to document, whatever disability you're dealing with, and come up with accommodations that will help prevent that from getting in the way of being successful in your classes. So that's an important support service to know about. College-wide policies, you can read through these. Non-discrimination policy, this should be pretty obvious. And again, this is on every syllabus you should have seen since you started at Clark. Title IX and sexual misconduct, and there's contact information in here. But for any of this, if anything ever comes up and you ever have any questions or concerns, you can always just come and talk to me, and I can take you through this and get you to specific people or specific contact information and so on. There's also help available, financial help, help with food and housing, and so on and so forth. We're still in a global pandemic. Our economy is still, trying to recover, and there's still a lot of uncertainty and a lot of fear out there. And if you're having trouble with, paying rent, getting enough food, if your car has broken down and you can't afford to fix it and you have no way to get to class, right? All kinds of things can happen. There's support services available through Clark, right? Coming in part from the CARES Act. So there's a bunch of contact information here, and again, you can talk to me and I can help you get through some of this information. Accommodations for religion or conscience. If you want to miss a class because of observing a holiday for your religion and so on and so forth, that is all protected in your protected rights also. So all right, we're going to be in person for most of the quarter, hopefully. So this is all also super important. So when you come to campus, right, you have to go through a health screening every day. Any day that you're coming onto campus, you have to basically go to the site and answer the questions. And it's really, really fast, right? But it's basically, a basic health check saying you're not running a fever, you don't have any symptoms that come from an unknown cause, et cetera, et cetera. And so that documents, your health status. Once you're on campus, 3-foot social distance at all times, wearing a mask at all times in indoor spaces. For the classroom, you're going to enter and leave classrooms in single file. Why? So that you can maintain a 3-foot distance. Okay. When you come in, there'll be hand sanitizer at the door that you can use to wash your hands. When you get to your desk or table, there will be cleaning supplies. You should clean the area before you begin class, and you should clean the area at the end of class. And all these supplies are provided. And if you have any questions about your health status, stay home, right? If you're feeling under the weather and you're not sure what's going on, stay home, right? Just send me an email, say, hey, I'm not feeling great, I'm going to stay home today. That's not a big deal. I'm not taking attendance this quarter, right? It's not a factor in your grade. And all of my lectures are recorded and will be posted online. So while I prefer that you actually come in to the classroom and actually, participate and be there live, I prefer even more that if you're not feeling 100%, you stay home, take care of yourself, and use the recordings to catch up on the material. All right, there's a bunch of other information around this that you can click through to here, having to do with vaccination. Everybody who's still enrolled in the class has either been vaccinated or has a exemption on file. If one of those is not true, you've been dropped from the course already and you wouldn't be here. So, but this has lots of additional information. This is a comment that we may move back to remote, just as we did this week. But the whole campus might move back at some point. Hopefully not. You have to keep your mask on at all times in class. You're not allowed to eat or drink in class. If you want to take a drink of water, you have to go outside, take your mask off, take a drink, come back in. All right. Keep social distancing, distances, and then this is all what we said before. Code of Student Conduct and Engineering Computer Science course policies. We've seen these before. This is just more specific information. All right, any questions about any of that?
I think there were a couple of questions in chat.
Oh, let me see. I don't have my chat window here. All right, let's see. So this will be an in-person class, but you know, if things come up and you know, you can't make it to class or something, you're very welcome to, you know, treat it as remote for whatever period you have to. So you can watch the recordings at your leisure and so on and so forth. The deadlines are still fixed though, right? The due dates for homework are still the same and so on and so forth. I'm requiring homework to be turned in online. So even though we're going to be in person, you're going to need to upload your homework to Canvas as a scan. And so if you're doing this remote for some reason, you know, that doesn't change the way you submit your homework. Also, we're completely full. We have 25 people enrolled in the course. If additional people add the course, they're going to have to do the course remotely because we can't fit more than 25 people in the classroom. So that's a possibility. Primary difference between 222 and 215. 222 is a programming course. It's a course in C programming where we're talking about data structures. So we're learning different ways of organizing information. Things like linked lists, hash tables, trees, different ways to sort and search, different algorithms, and so on and so forth. 215, this course, is studying sort of the theory behind all of that stuff. It's looking at some of the mechanics of mathematics and logic that can be used to understand things like linked lists and binary search trees and recursion and things like that. There's, you know, one programming assignment in this course, but that's it. Everything else we do in this class is going to be done pencil and paper, basically. So yeah, it's more logic, proofs, mathematics focused, yeah. More abstract concepts, exactly. All right. If you're not in 224 or 222, there's a little one-page or two-page how-to quick start guide in Canvas that basically you can use this to know how to log into the Linux machine. So the one programming assignment, we'll talk about this more when we're closer to that being due. But I'm going to test your code on our Linux server, which is linuxengrcs.com. And this will just tell you what your username is, what your default password is, different ways to log in, and so on and so forth, how to change your password. It's just basically, you know, the mechanics of what you need to know about using the Linux machine. If you've already done 224, you're in 222, there's nothing new here. All right, there's a link to the textbook. There's a link to the additional textbook. This should click through to the lecture videos. And so this is all of my CSE engineering courses for 2021-22. So this already has, you know, lectures from CSE224 and from CSE215 in fall. But I'll keep adding this quarter's lectures to it. So you can find those. There's also an index of topics. So, and you know, you can just search this by searching in your browser. And it'll link you to a date and a timestamp in a video. So if you need to go back and find things. There's also a Discord server. Doesn't get a lot of use for CSE215, but it's unmoderated. It's very informal. It's basically just a place where students can sort of chat and communicate with one another. It's a really good resource for, if you're kind of stuck on a concept and you'd like to ask some of your classmates for help. Or, there's a lot of students who graduated last year that are still on this server, and sometimes, one of them will have, some nice insight on a topic that might be useful to you. So it's a good place for, I'm really confused about, induction. What's the difference between the base case and the inductive step, right? And that's a general question that somebody might be able to give you some insight on, right? Now, you're always encouraged to talk to me with questions, right? But sometimes, somebody else will have a better way of explaining something, and that might be really useful. So you can link through the Discord server here. There's an invite if you haven't been on there before. All right, homework must be submitted on time, online to receive a grade. There are no slip days for homeworks for CSE215. There's no slip days for the course at all. Okay, CSE222, I give people 4 slip days, which they can use as they wish to turn in programming assignments late. I'm not doing any slip days for this course. Okay, so the homeworks have to be done on time. The reason being, we only meet twice a week, and if I'm expecting you to have, finished the homework and understood a certain set of concepts at the beginning of Wednesday's class, I'm going to start building on that. And if you decide you're not going to learn that previous stuff until Thursday, you're losing, the entire 2+ hours of lecture. Plus, I would have to postpone everybody for another 5 days before I can talk about the homework, and I don't want to do that. So homework has to be turned in on time. It's turned in online as a PDF upload. So write your homework up, scan it, upload the PDF to Canvas before the due date. And there's a guide here on how to write up homework. And this is important. Okay, and I guarantee if you follow these guidelines in other courses, your teachers will love you. Right? They will be shocked at what fantastic homework I get from this student. This is mostly common sense stuff. Okay, but since you're going to be writing this stuff up and turning it in, it's really important that I be able to follow your work and understand what you're doing. And that's mostly what this guide is about. So it's a one-pager. You can read through this, but the basic idea is you want to work in a well-organized way. Okay, so do your homework neatly. If you have to cross something out, put a single line through it. But, better yet, work with pencil and paper. Right? Get a nice, sharp, soft lead pencil, get a good eraser, and erase things completely. Along those lines, a lot of what we're doing in this course is going to involve trial and error. Okay, so it may sound like needless work, but work on scratch paper or a whiteboard or a chalkboard or something, and figure out how you're going to do the problem, and then when you're done, write it up neatly, right, as part of your homework. And this lets you write from beginning to end and lay things out logically, and that will actually help your understanding, right? In addition to making it possible for me to read it and follow your work, it'll actually help you to sort of see in your own, writing and your own creation, the complete process from beginning to end. Whereas when you're trying to do a problem like a proof, you might try 5 or 6 different things, come down here, have to back up, do something else, have to go back to the beginning and take a totally different track, right? And when you're done, you've got the answer, but you may not be clear how you got there. So now what you do is you go back and you try to write down on your homework that you're going to turn in the nice, complete, concise path from beginning of problem to final solution. And that can really help you solidify. No, you do not have to use month, /day, year. We don't want to get that whole conversation going in Discord again. Even though I say do that. But make sure you include the month, the day, and the year in some format. All right, so cross out neatly or use a good eraser. Print instead of cursive, unless you have really beautiful cursive handwriting that there's no doubt I can read. 8.5 by 11 paper, well, I don't care about that since you're turning in PDFs. So that's fine. Lined or unlined paper is fine. One thing that can be nice is to use unlined paper, but put a piece of lined paper underneath it so you can see the lines, and it helps your writing come out, you know, in horizontal rows. But then, you know, when you take that paper out from underneath, it looks like you wrote on blank paper. Have fun with it, play with it, you know. Standard engineering paper is fine. That's the green stuff with the grid on the front and so on. Put your problems in order, okay? You'd be amazed at how many times I get homework and, you know, here's questions 1, 2, 3, 4, 6, 7, 8, 9, 10, and at the end is question 5, you know. And if question 5 is the question I'm grading, I look at that, I see 5 is missing, I put down a 0, right? And then the student will write back and say, oh, question 5 was at the end, so I got to go back and look at the end and so on. Do your questions in order, right? And if you're writing your homework after you figured out how to do it, right, you can do the questions in any order that you want, because you're not turning in the paper that you're doing the problems on, you're turning in the paper that you're writing your final solutions on, right? Single-sided, again, PDF, it doesn't matter, but if you write on both sides of a thin sheet of paper, it can be really hard to read once you submit a scan. So take a look at the PDF you're turning in and ask yourself, is this easy for the teacher to read? Or do they see like my backwards writing from the other side of the page that makes it difficult to read what I'm doing on the front, right? All right, and then page layout, right? So at the top of the page, put your name, put the class, the homework number, the current date, and the page number, like 1/5, 2/5, etc. if this is a 5-page submission. But please put all of this on the top of every page, right? It's really, really helpful to me. And particularly when you turn this in person, this is going to be super critical. All right, don't worry about the staple because you're turning in a PDF. Left margin should be empty except for a problem number. So we'll be doing things like, you know, chapter 3, section 2.5, question 1, part A. Okay, I don't care how you do that, but I would like to be able to look at a page and know exactly what problem I'm looking at. So you know, 3.2.5.1a or something like that, but make sure I know what problem I'm looking at. Okay, and put that in the left margin and leave the rest of the page, rest of the margin empty. Right, so that's really easy to know what problem I'm grading. Work from top to bottom, right? Don't put an arrow partway through that goes up to the top to say, okay, and now I'm doing this thing up on the top, right? Put your stuff in order, and just work from top to bottom. Don't get to the bottom and go up to the next column of the page and work down, and then go up and work in the third column. Start at the top, get to the bottom. When you get to the bottom, go to a new page. All right, and finally at the end of your work, if there's a single answer, circle it or draw a box around it or somehow mark it so that I can see the final answer. But mostly I want to see your work leading up to that answer. A lot of questions may have, you know, a whole page worth of calculations followed by the final answer, which is 2, right? So if all you do is you write down the answer 2, you're not going to get any points. I have no way of knowing where that came from. I got to be able to follow your work. But I also want to see the final answer on a quick glance. And so I want to see like a circle around it or a box or something like that. All right, someone said, can I do my homework on an app like iPad or GoodNote? Yeah, you're welcome to do that. I don't recommend it though. Unless you happen to be one of the rare people who's really, really, really efficient with doing that, I would say no. I would say write it up by hand. The modality of doing a proof by hand will trigger in your brain differently from typing and formatting commands and so on and so forth. And I don't want you spending any brain power trying to figure out how to create a Greek character or how to put something on the top of a summation symbol, right? I want you to spend your brain power trying to understand discrete structures. So I'm not going to disallow using, you know, apps to create your homework and stuff, but I would say I think it would be better not to do that. Just stick with pencil and paper. All right, you're welcome. All right. So your first homework is due on the 12th, which is a week from Wednesday, and it comes from the textbook, Chapter 1, and it's just these problems. So section 1.1, do questions 2 and 4. 1.2, do question 4. 1.26 and 1.3, question 2. And we'll take a look at these on Wednesday once we've actually talked about some set theory. We'll look at these and I'll clarify some of these specific notes. But in general, each week, a homework will post. It'll be due at 1 p.m. on Wednesday, so that's right at the beginning of class, and it's submitted as a PDF upload. So write it out on paper, take a picture, scan it, do something, save it as a PDF, upload that to Canvas. And it's 1 p.m., so it's the beginning of class, right? In this case, on the 12th. And it's basically one homework a week for 9 weeks. All right, midterm is February 2nd. Final exam is on the Clark schedule, which will be on March 16th, 1 o'clock to 2:50 p.m. For any of these, if you have an extended time arrangement, you'll want to take your test at the DSS office, because they'll usually be classed, after the midterm, and you don't want to be trying to take your exam while we're lecturing and stuff. So you need to make arrangements to take your exam at the DSS office, and you just take whatever extended time you have, and the midterm and final yeah, so for the midterm and final, those will be actual physical pieces of paper. So I'll hand out your exam with pages with questions on it, and you'll write your answers on it. But homework is still uploaded. All right, so for the midterm and the final, closed book, open note. All right, so so this is a little different from what I've done in other classes, if you've had classes with me before. So your exams will be closed book but open note, and you're allowed 6 double-sided pages of notes or 12 single-sided. You can type them, you can print them with a computer, you can write them by hand, you can mimeograph the entire book and shrink it down to the size of a thimble, whatever you're into, okay? But that's all you're allowed for on the exam is your 6 pages of notes. Midterm will be 55 minutes, so 1 o'clock to 1:55. Final exam will be an hour and 50 minutes. So that's your 1 o'clock to 2:50. And programming assignment we'll talk about in a few weeks when we get into that unit, which is number theory. All right. Any questions? Any other questions on kind of the whole administrative side of things? And while we're remote, you're welcome to talk through the chat window. You're also welcome to use your microphone. If you have a question, you can just turn your microphone on and talk freely. When we're back to the classroom, right, we're not going to be doing Zoom, so if you want to say something, you're going to have to just sort of, speak up or raise your hand and speak up or that kind of thing. And hopefully we're going to keep this class pretty interactive. As opposed to just listening to me talk for 130 minutes.
We'll have to actually talk in class?
I know, shocking, right? Yeah, it's been so long since I've taught in person. It's going to be really nice to get back. Definitely looking forward to it. All right, well, let's talk about what this course is, or some of the things that we deal with in this course. So like I said, it's a combination of some math, some logic, some computer science, and some weird stuff, right? So math, we're going to talk about functions, right? Well, we know what functions are, y equals x squared. Well, that's a function, right? We're going to talk a little about probability, number theory, sets, sequences, matrices, counting, things like that. We're going to talk a lot about logic, and a lot of our logic is going to be related to doing proofs. So thinking about theorems, what is a theorem? How do we prove that something is a theorem? In other words, prove that something is true in all cases. So that's the logic part of the course. Computer science, right? Everybody who's in here has done Engineering 250 or the equivalent of Engineering 250. So Boolean logic, Boolean algebra, digital logic, those kinds of things will come into play. Graphs and trees, things that we'll be talking about in 222. Algorithms, finite state machines, regular expressions if you did 224. All of that stuff, you know, is in the domain of discrete structures. So we'll be dabbling in a lot of different areas. And then there's the weird stuff, right? There's the paradoxes. There's looking at different sizes of infinities. There's you know, looking at limits to what we can do with a computer. Are there problems we cannot solve with a computer? Can a computer understand itself? How does this relate to self-awareness in humans? I mean, all kinds of weird things, right? And so that's the weird part of the course, which I used to do on Fridays, but we don't have Friday meetings, so a lot of those will happen on Wednesdays instead. So let's start with the title of this course, Discrete Structures, right? So what do we mean by discrete? What do you think of when you hear the word discrete? What might that mean?
Below the surface.
Below the surface.
Visible.
Say again?
Not easily visible.
Not easily visible. Okay.
Finite quantity.
Finite quantity. All right, I'm hearing lots of good ideas here.
Individual.
Individual. So here's a series of dots.
Of what?
And there's...
People really messed up discrete and discrete.
Yeah, that's okay. So here's a set of dots. There's a finite number of them, right? So between this point on the paper and this point on the paper, there's only 5 dots. It's a finite number. They're individual, right? I can see that this dot and this dot are separate, and there's no dots in between them, right? This is very much a discrete type of situation. And yeah, it's a different version of discrete from, like, you know, being discreet about something. So don't mention, you know, the person's funny hairdo. But this is discrete like individual. Now I can draw another set of dots between this point and this point, like this. And, you know, in some ways of thinking about it, this is a whole bunch of little tiny dots really close to one another, right? Maybe these dots are like, you know, molecules of ink, or maybe they're infinitesimal. And maybe there's an infinite number of dots between here and here. And it's very hard to separate one dot from another. And if I pick out 2 dots like here and here, there's still more dots in between. And so this is not discrete. This is what we would think of as continuous. And these are kind of, you know, 2 extreme points. Discrete versus continuous. And a lot of what we do in our math classes, like, you know, algebra and trigonometry and calculus, is dealing with continuous stuff. Most of the math we do, we deal with real numbers. If you take 3 and you divide it by 4, you get 0.75. If you take 1 and you divide it by 7, you get a big long fraction that goes on forever. But in a discrete setting, we might just deal with things like, you know, whole numbers. And this is in some ways a pretty minor change, right? This is just, a subset of that. This is, just picking out some points that we're going to consider and throwing away others. But in other senses, this is a fundamental shift. Things are very, very different when we're in a discrete realm versus a continuous realm. And there's huge branches of mathematics that sort of fork off from one another, depending on whether we're thinking discrete or continuous. So we're going to mostly deal with discrete, which means mostly we're not going to deal with real numbers. We're mostly going to stick with integers. Sometimes just, positive integers or whole numbers that include 0 or maybe positives and negatives. But stuff with space in between them. And historically, so we'll do a little 3-minute history. Historically, right, how did people figure out what numbers are? Why did people start talking about numbers? Most likely it was because they wanted to count. Right? So there's, 2 wolves over here. That's important to know as compared to there's 20 wolves over there. Right? And, you'd never find a situation where there's, 2.5 sheep in my field. So most likely people developed the notion of numbers for the sake of counting. And when you're counting things, you're really thinking about, positive integers. And even though the Egyptians apparently knew about 0, the Romans apparently didn't. Because 0 doesn't really pop up when you count things. You can't count 0 elephants in the room. I mean, you could. There are 0 elephants in my room right now. But that's not what people do. And so 0 is somehow different from 1, 2, 3, 4, 5. And this notion of, 3/4 of a sheep, which as someone said, unless the wolf got to it, 3/4 of a thing is a fundamentally different concept. Right? I mean, I have a pen here. Is it possible to have half a pen? Well, I mean, I could break it in half, but neither half would be a pen, right? I just have something spilling ink on my page, right? It doesn't make sense to talk about a half a pen or a third of a pen or 9/10 of a pen. And so these things are kind of elusive, and even weirder are these things like, -2 sheep. I mean, what does it mean to count -2 sheep? And if they walk into a field where there's 2 sheep, now you have 0 sheep. I mean, that's just madness. So a lot of what we think about in discrete structures comes from, sort of this kind of canonical notion of numbers and what they are and what they're for. But as we generalize from here to here to here to here to here to some even weirder things, we'll develop these concepts. Yeah, anti-sheep, exactly. All right, so that's just something to kind of keep in mind in what we're doing, and we'll refer back to this notion of discrete again and again throughout the course. But let's go ahead and start with the first chapter of the text, which is dealing with set theory. And so this is our first major topic. By the way, I'm going to take a break around 2 o'clock. We'll take like a 5-minute break just to stretch our legs and such. But let's start with set theory. So let me begin with a definition. We're going to do a lot of definitions in this course, and again, I'm recording these lectures. These lectures will be posted, so you can refer back to this. But I encourage you to take notes as the course progresses, as we go through lecture. You don't have to write down everything I say, And if there's something you wish you had written down and you didn't, you can go back to the recording and see it later. But writing your own version of what I'm saying can help you, code it in your mind in a way that makes it easier to understand. So you're encouraged to, do note taking in the usual way. So let's start with defining a set. So a set is a collection of things. Well, that seems pretty harmless, if not uninspired. It's a collection of things. So, I could have a highlighter and a Sharpie and a Hello Kitty sticker. And that's 3 things, and that forms a set. I could, have a highlighter, a Sharpie, a Hello Kitty sticker, and a mouse. That's a different set. And so we can take this sort of naive notion of a set as just a collection of things without too much concern for what kinds of things we're talking about. They could be pens, they could be stickers, they could be things with batteries inside. And this is a version of set theory that's called naive set theory. And we'll see what the possible danger is in using this word things. If we're not a little more careful with what kinds of things we can put into a set, we can get into paradoxes. And we'll talk about some paradoxes in another lecture or two. But for now, we'll just think of a set as a collection of things. And a collection just means, it's a set of things. So in particular, sets are unordered. There is no such thing as the first element of a set or the second element of a set. So let's suppose I have a set consisting of a circular slide rule and a Hello Kitty sticker. Alright, that set is exactly the same thing as this.
Isn't that technically like 8 Hello Kitty stickers?
Oh, let's call it 1, but yeah, technically, did you actually count those? You
No.
did. Okay.
Was it 8?
Yeah, I think so.
Man, wow.
Impressive.
Okay.
Alright, so this set is exactly the same as that set, exactly the same as that set, exactly the same as that set. Right? There's no notion of order of these things or placement of these things. It's simply the reality that this is part of the set and this is part of the set. And out of everything in the universe, these are the only 2 things that belong to the set. Okay, that uniquely defines this set, this collection of things. And if I happen to place them like this, that's completely irrelevant. Alright, so it's just a collection of things, and the essence of a set is basically, for everything in the universe, is it a member of the set or not? Well, this set that I'm talking about, there's only 2 things that belong to it, the circular slide rule and the Hello Kitty stickers. And that's it. Alright, so we'll come back to this notion of unordered in a few minutes. So let S be a set. And a lot of times we'll just use, a letter, usually an uppercase letter, to represent a set. So in this case, I'm imagining I have some set called S. Okay, for any object, so instead of things, let me use the word objects. These are not like, object-oriented programming objects, just objects. For any object X, either X is a member of S or X is not a member of S. So if I have an S, a set, think of it as S, and I think of an object, that object either is in that collection of things that make up S, or it's not in that collection of things. Right? And there's no other possibility. It's a collection of things, so if I pick, you know, a silver fountain pen, I can say, does this belong to that collection? Is this a member of the set S? And the answer is either yes or no. And that's sort of the most basic property of a set. Things either belong to it or they don't belong to it. So we have some symbology for this. So if X is a member of the set S, we write this. X, and we use a little epsilon symbol to say belongs to the set S. Let me write that more cleanly. X is a member of S. And if X is not a member of S, we write that epsilon symbol with a line through it. So X is not a member of S. And so this is set membership. All right, well, I gave you a few kind of quirky examples of sets. What are some other examples of sets that we may actually deal with more often in this course? The set of all integers, the set of even numbers, the set of prime numbers. A prime number is a number bigger than 1, an integer bigger than 1 that has no factors other than itself and 1. So 3, 5, 7, 11, 13, 23, 101, these are prime numbers. 25 is not prime because it's divisible by 5, for example. So integers, even numbers, prime numbers, multiples of 237. Well, that's a set of integers, but it's only some integers. 237 is in there. 474 is in there. 500 is not in that set because it's not a multiple of 237. All right, so how can we describe sets? We can say, you know, the set of even numbers or a set of multiples of 237, but we want something more universal, something that we can write down that other people will understand what we mean by a particular set. And so one way to do this is to list the elements of the set, and we do this inside curly brackets, and we separate the elements with commas. So S could be the set containing the letter A, B, the number 17, a square, a smiley face, and -2 and 5 and the letter X. So there's a set containing 8 things. And this is pretty unambiguous, right? Except it's not clear what the universe is that I'm picking things from here. I guess anything that I could think of. But you know, this has 1, 2, 3, 4, 5, 6, 7, 8 elements. And A and B are members of S, and the letter Q is not a member of S. Sorry, was there a question or comment?
Well, I just said your imagination.
Yeah, my imagination is the universe. That's a scary thought. All right, so that's one way to describe this. But you know, a lot of sets have too many things to list. For example, a set of all positive integers is too big to list all the positive integers. So sometimes we might write something like this. One, 2, 3, 4, 5, 6, ... And this can be a little tricky to use. Now, most of us, if we're in this course and we've been doing this for a while and we see this, we're going to assume this is the set of all positive integers. We're going to assume that dot 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 means 7, 8, 9, 10, and so on. But if I list something like this, well, is 9 a part of this set? Maybe, maybe not.
I would think so, given that it's going up to via odd starting with 3.
Yeah, this is the odd numbers bigger than 1, right? But maybe it's the set of odd prime numbers, which would also include 3, 5, and 7 as 3 elements, but not 9, right? So this may not be totally clear. If we were in a unit dealing with prime numbers, you might be confused as to whether or not this is all the odd numbers or just the odd prime numbers. So you got to be a little careful with this dot dot dot, and we'll try to use it only when it's really, really clear what we mean. And most of the time when we use it, it's going to be, you know, for something like this, where it's just consecutive numbers, and we don't want to list out, you know, an infinite number of integers, so we list a rule. And we could do something like this. With a dot 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 on both ends. And here it looks like I'm trying to say the list of all integers, positive, negative, and 0. So, you know, 0, 1, 2, 3, and onward, negative 1, negative 2, negative 3, and onward. So that, you know, looks pretty reasonable for the set of all integers. Positive, negative, and 0. But we could also do something like, you know, I could have some set T equals the set of all positive integers. Well, that's pretty clear what I mean there, right? I could say the set of all x such that x equals 2 times some integer. The set of all x such that x equals 2 times some integer. Well, what sorts of things would be in this set? What's an example of an x that's 2 times some integer? Can you think of anything that's twice the value of an integer?
2.
Yeah, 2 is 2 times 1. What else?
4.
Yeah, 4 is 2 times 2. And 6 and 8 and 10.
Yeah.
Anything else?
Well, it's just even numbers.
Even numbers after 1, or well, after 0 technically.
Well, so 0 is also an integer. So 2 times 0 would be 0, so 0 should also be in here.
0 is in there.
And negative 1 is also an integer. And so 2 times negative 1 would be negative 2 is in there. And negative 4 and negative 6 and so on.
I guess it's just even numbers. Huh?
So it's actually just all even numbers. So we could write it as the set of all even numbers, or we could list these and hope the person sees the pattern. Or we could say the set of all x such that x equals 2 times some integer. And this is a notation we'll use fairly frequently. It would actually write it as a set of all x, and the colon means such that. And you'll see this as either a colon or a bar sometimes. It's a set of all x such that x equals 2 times n, where n is an integer. Or you could do the set of all x such that x equals 2n, n is an integer. So that's another notation we'll see. All right. Alright, a really nice kind of set that's very easy to describe is a singleton set. A singleton set is a set with a single element. It's a collection of just one thing. And so, for example, here's a singleton set containing one element A. Here's a singleton set containing the number 5. So singletons are a pretty easy set to actually write, as long as we can write down, you know, something that represents the thing that's in the set. We just list that one thing inside curly brackets. There's an even simpler set, and that's called the empty set. That's the set containing nothing. And that is a valid set. It's just a set that nothing happens to be a member of. For example, I could say, you know, x equals the set of all I such that I is bigger than 0 and I is less than 0. Well, there are no numbers that are bigger than 0 and also less than 0. And so this would be exactly the empty set. Has no members. This is a really useful set, and it's so useful that we actually have a special symbol for it, which is a 0 with a slash through it. So this is a good time to mention that we'll use a lot of notation in this course that you may have seen before or may have used in a different way. And even within the course, sometimes we'll repurpose notation. When we discuss set theory, we may use a symbol to mean something, and then when we talk about functions, we may use the same symbol to mean something else. So context will be important. And you know, sometimes if you write kind of sloppy like I do, you put slashes through your zeros so people don't think it's the letter O, right? Well, that's not what this is. This is a symbol in set theory, which means the empty set, set containing no elements. All right, so let's do a quick break. It's 2:07. Let's take a 4.5 minute break and stretch your legs if you like, and we'll come back and we'll start looking at some more specific examples of some useful sets, and we'll build up from there. All right, so I'll be back in a few minutes. I don't know if you can see my bird feeder from there. Probably not. Oh well, there's birds out there. Alright, welcome back. Alright, so let's look at some particular sets that we're going to use a lot in this course. Probably the most common is written as a Z with this funny sort of double line going down the diagonal. And this is the set of all integers. So it's things bigger than 0, things less than 0, and also 0 itself. So this is, you know, like this. And it definitely includes 0, that's really important, and it includes negatives. There's a set n with this double line on the n, and that's the set of natural numbers. And that's integers bigger than or equal to 0. And there's some ambiguity as to whether or not the naturals actually include 0. In some texts they start from 1, in other texts they start from 0. So I usually won't use this notation, and if you see this notation used or you hear someone talk about the naturals, you want to make sure you understand whether or not it includes 0. But it's you know, numbers that don't include things like negative sheep or fractional sheep, but may include, you know, the notion of 0 sheep. So they're like the numbers that occur in nature in some sense. This R with a double bar on the vertical, this is a set of real numbers. And so those are, you know, positive, negative, 0, but they can be fractions, they can be decimal numbers, and so on and so forth. And it can include weird numbers like pi, for example, which there's no fraction that represents pi, but it's still a real number. So these are the numbers we usually deal with in sort of calculus or physics, and they're the numbers that you can pop into your calculator, basically. This Q is the set of rational numbers. These are basically fractions, or real numbers that are equal to fractions. So 1/2, 1/7, 2/3, -5/19. Those are rational numbers. Is the number 5 a rational number?
No.
Yeah, it is. It's 5/1.
Yeah, it is. It's 5/1.
Yeah, that makes sense.
That's a trick question. So yeah, 5 is contained in the set of rationals. In fact, all the integers are contained in the set of rationals. But there are definitely rational numbers like, you know, 1/2, which are not contained in the integers. So the rational is in some sense a bigger set than the integers. It includes all the integers. We'll make that precise in a little bit too. The set we rarely talk about are the complex numbers. The complex numbers are like real numbers, but they also include this mysterious I, which is the square root of -1. So if you go back to some of your other courses, or maybe some engineering work, there's no real number whose square is -1. Because when you take any number and you square it, you always get something at least 0, generally positive. So if we just create this new imaginary number I that we call the square root of -1, and we add that to the reals, we got this larger set called the complex numbers, and that's a C with the double vertical bar. We won't really deal with that in this course, but there are other courses where you could deal with that a lot. All right, so those are some predefined sets we'll deal with often. Usually the integers and rationals, occasionally the reals, and it's useful to have notation for those. Another thing that we can use to describe sets is something we call interval notation. So I can write a pair of numbers inside square brackets, and that means the set of all numbers x, typically, you know, numbers x contained in the reals, such that x is bigger than or equal to a and x is less than or equal to b. So if we want to represent, you know, all the reals between a and b inclusive, we can just write a comma b inside square brackets. If I use parentheses, that's almost the same set. But it doesn't include those endpoints.
So very similar to like coordinates and such, or not coordinates, but like in math and stuff, you do that.
Mm-hmm. Yeah, exactly. And so if we had a number line, and we wrote down, you know, bracket 2 comma 5, that would mean all the stuff on the number line between 2 and 5. Right, so all of this stuff, including 2 and 5 themselves. And if I write it with parentheses, well, it's almost the same set. We're really just missing a couple of points. We're missing the number 2 and the number 5, and so sometimes you see a little circle drawn here that says, oh, 2 and 5 aren't actually included in that shaded out section, but everything in between is. This, by the way, is called a closed interval, and this is called an open interval. And the nomenclature is like, you know, this is sort of, it reaches the end, so it's kind of closed on those ends, whereas this is kind of open. It doesn't quite get to those endpoints there. But as simple a distinction that is, there's something fundamentally different about these two sets. So think about this set up here, this closed interval between 2 and 5. What's the smallest number in this set?
2 and 5. Or the smallest is 2.
Smallest number is 2. What's the smallest number in this set?
It could be like, or it'd be like point infinite.
Yeah. Which isn't really a number, right?
No.
There really is no smallest number in this set. And that's pretty freaky. Because if we just kind of naively think of a set of numbers, right, and we know every number in there is positive, we should be able to figure out what the smallest number is. Well, there is no smallest number in this set. It's not 2.00000001, because there's numbers smaller than that. In fact, there's an infinite number of numbers smaller than that number I just named. And that's a fundamental distinction between an open interval and a closed interval. And if you take that distinction and you run with it, you can develop a set of mathematics called point set topology, which is kind of like an abstract version of calculus. So a lot of math comes out of this simple distinction. We're not going to worry about that. But I just kind of mention it as a recurring theme of something that seems very, very simple and straightforward on the surface, often has a lot more going on underneath. So yeah, the open interval that excludes these has no endpoints, that's right. Alright, and the other thing, this is not terribly startling, we can do like half open intervals. Like bracket A, comma B, close parentheses, and it's sort of the canonical x is bigger than or equal to A and x is less than B. So the parentheses basically mean excluding the point, the square brackets mean including the point. So this would be a half open or half closed interval. Alright, well, a set is a collection of things, and I said we're not going to be too careful about what these things are. So what if those things are themselves sets? So let's make a set T consisting of the set of integers and the set of reals. Is that a valid thing to do? Absolutely. Might not be a lot of fun to think about, but this is a perfectly well-defined set. And T has two members. There's two things contained in this set. The first thing is the set of all integers. The second thing is the set of all reals. And that's perfectly valid. So sets can contain sets. I could make a new set, S, that contains the set T and also the set of integers. And this is a perfectly well-defined set. It has two elements. One element is the set of integers, the other element is the set T, which itself is a set containing the set of integers and the set of reals. But we don't need to think very deeply about what these things mean, right? A set is just a collection of things. If I tell you this set contains T and Z, that's all you gotta know. It contains T and Z. Does this set contain the reals? No. It contains T and it contains Z. That's not the set of reals. That's not the set of reals. So the set of reals is not a member of this set. But if we think a little deeper and we think, well, this contains T and T is a set containing the set of reals, we might mistakenly believe that the set of reals is a member of S. It's not. S has only two members, T and Z. Not the reals, not the reals. So sometimes in this course, you know, this is a course, there's a lot of math, logic, computer science. Those are very precise disciplines, right? But sometimes it's going to be beneficial to not think too deeply, especially when we start talking about logic. Because a lot of times we'll find our intuition will run contrary to logic. And if we start following our intuition, it may convince us to move astray from logic, from reason. And maybe here, you know, it feels like, well, there's an R inside T and there's a T inside S. I think R should be a member of S. And we may, you know, want to believe that R is an element of the set S, but it's not. And if we forget that, you know, T contains Z and R, and we just think, you know, T is a set, Z is a set, neither of those is R, we'll correctly conclude, okay, R is not a member of S. And this will pop up again and again. And so part of the challenge of this course is kind of being able to follow your intuition up to a point And then maybe being able to abandon our intuition and just kind of follow the bare mechanics of a logical proof, for example. And then know when to come back in and apply our intuitive understanding to take the bare mechanics of a logical proof and apply it to something that we're trying to demonstrate, for example. So here's a general disclaimer / warning for this course in particular, and this probably applies to a lot of other courses. But a lot of what we're doing in this course is going to start with things that we're already familiar with. Most of us have heard about sets before, and we understand what a set is. We're going to spend a week talking about counting, right? 1, 2, 3, 4, 5. And most of us know how to count things. So a lot of the stuff we do in this class will begin with something that we're very familiar with, and something that we think we understand very well because we've been doing it our whole lives. But if you stick with me and go along for the ride, we will turn these familiar concepts into things that look very different and that have some very startling and surprising characteristics. And the danger can be, you know, if you say, well, I already know set theory, we learned that in 7th grade, right? You may blink and suddenly realize that, like, what we're saying has nothing to do with anything you've ever seen or heard before, and you're completely lost, right? Which is a good time to, you know, ask questions and say, hey, I think I spaced out for a minute. Can you go back and tell me what just happened, you know? Or come to office hours and do the same thing. And so this will be a recurring pattern in this course. And so set theory, we're going to, you know, spend some more time developing kind of the mechanics of it, but we'll take it into some strange directions. All right, so far we've been working with just like one set. Here's a set, here's a set, here's a set. So let's start dealing with multiple sets. So let's talk about equality of sets. So if I write A equals B, just using a plain old equals sign, this means A and B have exactly the same elements. Oh, if you're in the least bit inclined towards abstract algebra, go for it. I can recommend some good books also. But it's a beautiful subject in my opinion. And we don't really get into it.
Abstract algebra?
Algebra where you're not necessarily dealing with numbers. So algebra, we have equations, we have addition, subtraction, we can solve, you know, 2 times x equals y, and so on. But we're always dealing with usually numbers, usually real numbers. But we can do all of those concepts where we're not restricted to real numbers. The things we're manipulating could be geometric shapes, they could be sets, they could be letters, they could be ways of arranging collections of objects. And you can develop algebra in a much more general sense than just algebra of real numbers. And some of it looks like the algebra we're used to, a lot of it looks like something very different. And it can get you into some really wonderful areas.
Very interesting.
Yeah, it's one of my favorite topics, actually. So if we say A equals B, it means A and B have exactly the same elements. So you know, the set 1, 2, 3 is equal to the set 1, 2, 3. Well, that's not very startling, right? It's also equal to the set 3, 2, 1. Why? Because the order of the elements is unimportant, right? This is simply a set containing 1, 2, and 3. This is a set containing 1, 2, and 3. It's exactly the same set. Alright, so if two sets have exactly the same elements, we can write the equal sign and say that they're equal to each other. Another way to do this would be to say A equals B, and I'm just putting this in quotation marks to be kind of like stylistically correct. So A equals B means X is contained in A if and only if X is contained in B. This is for all X in whatever universe we're talking about. If we're talking about numbers, it means any number is contained in A if and only if that number is contained in B. And this if and only if will pop up enough that we have a special symbol for it, just IFF. Means if and only if. Alright, one other stylistic thing to be careful of up front. When you're writing the elements of a set, never list an element more than once. It's meaningless. Right? This is not a proper way to write a set. If it was, this would be exactly the same set as this. But when you write a set in this notation, what you're doing is you're listing all the elements that belong to the set. Well, I'm saying, 1 belongs to the set, and 2 belongs to the set, and 3 belongs to the set, and 2 belongs to the set. Well, don't do that, right? Who's coming to lunch? Bob, Betty, Jane, and Bob. Right, well, if I already listed Bob, why would I list Bob twice? So don't list the elements of a set more than once. Either list the element to say it belongs to the set, or don't list it to say it doesn't belong to the set. Alright, we'll see a reason why I mention this in a little bit, because sometimes there's a temptation to list elements twice. Alright, good time to mention another thing that you're probably familiar with, which is Venn diagrams. So a Venn diagram is a useful way to sort of visualize what's going on with sets. It's not a precise tool for doing proofs, but it is a way to help us visualize what might be going on with some sets or some set operations so that we could construct a formal proof. So it's an aid for us to help understand something. So here's a typical example of a Venn diagram. So we start off with the universe. And our universe might be the set of all integers. But you got to know what the universe is. Could be the set of all integers plus cookies that have chocolate. But you got to know what the universe is. And then we can draw, typically a circle for different sets. So this could be the set of, positive integers. And this could be the set of even integers. And they're both part of the universe of the set of all integers. And there's some overlap here. Because, some even integers are also positive integers. But there's also some positive integers over here that are not evens. And there's some even integers that are negative. They're not positive. So by drawing my circles like this, and the shape of the circle isn't meaningful, but the fact that these overlap tell me that, hey, there's some stuff going on. There are some things that are both positive and even. And there's also some stuff that's, even but not positive, and some stuff that's positive and not even. And I could draw a set over here, which could be the odd integers. And I can say, hey, you know, there's some odd integers that are positive, there's some positives that are odd. But there's also positives that are not odd. I can also see, hey, the evens and the odds don't overlap. There's nothing that's an even integer and also an odd integer. And you know, I could have some set S for small, which contains 2, 4, and 6. And S might be sitting right here. Everything that's in S is also in this bigger set of even integers. Well, I guess it would be in the overlap also. So there would be S. Everything in S is an even integer. Everything in S is also a positive integer. So Venn diagrams, you've probably dealt with them before, right? But it's a way to visually understand sometimes what's going on. And like I say, we don't do proofs with Venn diagrams, but it's a way to sometimes get an insight into how sets are related to one another. And that insight might lead us to create a more formal proof. Alright, so let's look at this notion of, like, you know, one thing being part of another thing, or two things overlapping. Let's try to formalize that. So our first notion is a subset. So A is a subset of B, and we write this like this. So A and then a sideways U with a line underneath. If and only if every element of A is also an element of B. So A is a subset of B if and only if every element of A is also an element of B. Otherwise, A is not a subset of B, and we can write that as a subset symbol with a slash. So for example, the set containing 2, 4, and 6, that's a subset of the integers. Because everything in this set is also in that set. Now there's things in here that aren't in there, that's okay. We're not saying these are equal. In fact, they're not equal. The integers are not equal to just a set 2, 4, 6. But everything in this set, 2, 4, 6, is also in the set of integers. But the set containing the numbers 2, 2.5, and 3, that's not a subset of the integers. Because this thing right here, 2.5, is not a member of that set. Alright, so here's a little factoid. For any set S, S is a subset of itself. Why is this true? When we say A is a subset of B, we're claiming every element of A is also an element of B. Well, to say S is a subset of S means every element of S is an element of S. Well, that's pretty obviously true, right? Every element of S is an element of S. And on the basis of that, we can say, therefore, S is a subset of S. And it doesn't matter what the set S is. It could be integers, it could be smiley faces. So every set is always a subset of itself. there's another fact that's a little more disturbing, which is that the empty set is a subset of every set. And this takes a little more thinking about. A is a subset of B if every element of A is also an element of B. So for this to be true, we need to know that every element of this is an element of S. Well, there are no elements in this set. So kind of in a vacuously true sense, every element of this set is an element of that set. Or put differently, there's no element in here that's not also in here. Because, by the way, there are no elements in here. So this turns out to be true also. So every set has at least two subsets, itself and the empty set. So that's a good thing to know. Every set has at least two subsets. And if you really want to get a little weird, we can observe that this is also true. And so technically, you know, every element has at least two subsets except the empty set. Because its only subset is itself, which is also the empty set. Alright, well because of this, we can define a proper subset. So we can say A is a proper subset of B. And we write that as A in the usual subset symbol, but we put a little slash through that horizontal bar. Okay, so A is a proper subset of B if and only if A is a subset, but it's not equal to B. So for example, 1, 2, 3 is a subset of 1, 2, 3. 1, 2 is a subset of 1, 2, 3. But we can also write 1, 2 is a proper subset of 1, 2, 3. So it means it's an interesting subset. Because we know, you know, a set's always a subset of itself. Not so interesting. But when we have a different set that's a subset, we can say it's a proper subset. So over here in our Venn diagram, since this was completely contained inside here, this set S was contained in the set of positive integers, this is a subset of that set. And any set that we draw inside another set, that's a subset. In fact, each of these is a subset of the universe. And the way I wrote this, all of these were proper subsets as well. Alright, so here's a little theorem which relates equality and subsets. So a theorem is just a statement that's true. And eventually we'll be proving theorems to, like, you know, prove that these things are always true. So theorem, two sets A and B are equal if and only if A is a subset of B and B is a subset of A. Okay, why would this be true? If A and B contain exactly the same elements, then we know that A is a subset of B. Right? Because if B is the same as A is a subset of A. We know that's always true. And if A is the same as B, we know B is a subset of B, so B is a subset of A. So if A and B are equal, both of these statements are definitely true. The other direction, if A is a subset of B, it means every element of A is an element of B. And if B is a subset of A, it means every element of B is an element of A. So these two statements taken together basically say A and B have exactly the same elements. That's what we mean by A equals B. So this is a theorem that basically comes just out of the definitions of equality and subsets. But it's useful because sometimes proving these is easier than just trying to prove this. We break the thing that we're trying to show into two sub-problems. This is another thing that'll pop up a lot in this course, and this pops up a lot in programming. You want to write a program to do this, and that's a big task. But maybe you can write a program to do this, and then put them together. And now you've got a program that does the whole thing. That's how we write code in pieces. That's why we have functions. That's how we modularize our algorithms. Well, same thing here. Sometimes we want to show this, and that's really hard to show. But we can show this very easily, and we can show this with a little bit more work. And then we can say, well, since we showed both of these, this theorem tells us that that's also true. And we'll do this a lot in this course. We'll break a problem down into a different kind of problem that's more solvable. All right, let's talk about sizes of sets. So here's a set containing 3 elements. Let me call this set T for 3. And here's a set F containing 5 elements. And here's, the empty set, which contains no elements. So a first measure of the size of a set is just to count the number of elements. This set has 1, 2, 3 elements. We could say the size of this set is 3. And this set has 1, 2, 3, 4, 5 elements. We could say the size of this set is 5. And we'll do this. We'll define the size of a set as just the name of the set with bars around it, like an absolute value symbol. And we'll say the size of T is 3, meaning it's got 3 things in it. The size of F is 5. The size of the empty set is 0 because it has 0 elements.
I have a question.
Yeah.
Does this include the subsets? Because every set has its 2 subsets, right? Or is it
Correct.
just we're talking elements straight.
Yeah, we're just talking elements because subsets are not actually elements.
Okay.
But we're gonna loop back to that in about 1 minute. So your timing is good. All right. So if we just count the elements, that gives us the size of it. So when we say if S is a set and we put S inside bars, this is equal to the number of elements in S. But we gotta be careful. If S has a finite number of elements, then this symbol here means the number of elements in S. But we got a different situation if S has an infinite number of elements. For example, if I take the set of integers, well, how many elements are there in the integers? It's an infinite number. And there's more than 3, there's more than 3 million, there's more than 3 trillion. In fact, there's more than any number I can name. So for a set that contains an infinite number of elements, this is not the number of elements, because that number doesn't exist. But for a finite number of elements, what we can call a finite set. So a finite set contains a finite number of elements. For a finite set, this symbol just means the number of elements. And that's all we're going to say about that for now. We'll come back to that in a few days. But this we can also call the cardinality of S. Cardinality is a fancy word for size. So when you write a set with bars on either side, that's a symbol representing the cardinality or the size of the set. And for a finite set, it's just the number of elements in it. So this set has cardinality 3, 5, and 0. Now we can define cardinality for infinite sets, but it's a very different definition, and we're not ready to do that yet. But we will come back to it, and it'll be glorious when we do. Alright, let's talk about subsets again. And let's suppose, we have a set S which is equal to, I don't know, 2, 5, and 7. We can ask the question, what are all the different subsets of S? So we can say, let's list the subsets of S are. Well, we know 2 subsets right away. We know the empty set is a subset, and we know 2, 5, 7 is also a subset. But are there any other subsets?
A combination of the 3 numbers,
Such as?
2 and 5.
Alright, there's a good subset, 2 and 5. What else?
2 and 7.
2 and 7. What else?
2.
And any
5,
other?
7.
There we go. So by sort of thinking about it and playing around, we can list 1, 2, 3, 4, 5, 6, 7, 8 subsets of S. And sometimes that's a useful thing to do. And so we have this definition, P of S, which is called the power set of S. And that's the set of all subsets of S. And so the power set of the set 2, 5, 7 would be a set containing 8 elements. The elements being this, and this. It's a set of sets. So we started with a set containing 3 elements. The power set is the set containing all the subsets of that original set. So this power set has 8 elements, and each of those elements is itself a set. And in particular, it's a subset of that original set S, 2, 5, 7. Another example. If S is the set 1, 2, the power set of S contains the empty set, the singleton 1, the singleton 2, and the set 1, 2. And those are the only subsets of S.
Weirdly, I feel like I'm working in binary again.
Yeah, isn't that cool? That feeling's going to come back a lot. Which makes 250 worth it, you know. 250 is really foundational in so many ways. And it's not the digital logic part. It's much deeper than that. So yeah, we'll get a lot of 250 flashbacks in here. So the power set of this set had 4 elements in it, right? The cardinality of the power set of S was equal to 4. Here the cardinality of the power set of S was equal to 8. And
What does cardinality mean?
Size
Sorry,
of.
you said that.
That's okay, size of.
Size of, okay, thank you.
So for finite sets, it's the number of elements. So somebody direct messaged me a little idea, a theorem, as to why this was an 8, and maybe why this is a 4. Anyone see a pattern yet?
Yeah.
Again, back to binary.
Yeah, back to binary.
2 to the n.
2 to the n. Right, if I've got 3 things in here, I've got 8 ways that I can list subsets of that. And so there's actually a theorem. If S is a finite set, then the number of things in the power set of S is equal to 2 raised to the number of things in S. So S has 3 things, the power set will have 2 to the third, which is 8 things. If I listed a set with 4 elements, any set with 4 elements, the power set would have 16, 2 to the 4th elements. We're going to prove this or see it several times over the next 10 weeks. It's just going to come up again and again when you least expect it. It's suddenly going to pop up. Alright, well let's look at edge cases. Edge cases are really useful in this kind of subject. Looking at things that are very big or very small can be useful. For example, the empty set has a cardinality of 0. There's no elements in the empty set. Well, if we believe this formula that we just scribbled, that the power set has 2 raised to the cardinality of S things in it, then the cardinality of the power set of the empty set should be 2 to the 0, while 2 to the 0 is 1, right? So there should be 1 thing in the power set of the empty set.
However, there's 2. Right?
Well,
Empty in itself.
yeah, except itself is empty, so that's that little thing I put in parentheses, right? That's the one case where it only has 1 subset.
Mm.
And so the power set of the empty set is a set containing the empty set. And this can be a little bit disconcerting. This is not the empty set. This contains 1 element, which happens to be a set, which happens to be the empty set. But this is a set containing 1 element. It's not empty. It's got 1 thing in it. I can see it right there. Right? So this is not the empty set. It's the power set of the empty set, though. And so sure enough, the empty set has 1 thing, right? The cardinality is 1. What if I take the power set of the empty set? That's the power set of this thing. Well, what are the subsets of this set?
The empty set.
The empty set, because that's always a subset. And there's one more.
Power set of the empty set.
Yeah. Or let me just write, you know, the set containing the empty set. And so the number of things in this is 2, which is 2 raised to the number of things in this, which is 1. So the power set of the empty set contains 2 things, the empty set and the set containing the empty set. Are you tired of hearing me say empty set yet?
Should we get used to it?
Nah. We're just having fun for the last 5 minutes. But yeah, we could keep going, right? We could try to construct the power set of the power set of the power set of the empty set. And that's the power set of something containing 2 elements. And we get the empty set, we'd get this, and we get a pair of singletons. The singleton containing that, and the singleton containing this set. And at that point, you know, we're lost. So, but we could do this, right? And we can develop areas of mathematics just by looking at power sets of the empty set. But we won't do that. It's a fun exercise sometimes. Alright, one more thing to go over. And then we'll call it a day, and then we'll start doing set operations on Wednesday. But let's squeeze in our last 6 minutes. Cartesian products. So to describe a Cartesian product, we need a new definition. So an ordered n-tuple is an ordered collection so we write it in parentheses instead of curly brackets, and it's going to contain n things. And ordered meaning the order is important.
Or table.
Tuple.
You?
Yeah, like Tupperware. N-tuple. Well, my camera is kind of like low-resing here.
Yeah, it's like weirdly,
Yeah, I think my saturation's
okay,
too high.
Yeah, saturated, that's what it is.
Alright, let's try that. Alright, so ordered n-tuple, it's an ordered collection of n objects. Right? And for 2 tuples to be equal, they have to have not only the same objects, but they have to be in the same order. So it's different from a set. Right? For example, the 2 tuple 1, 2 is not the same as the tuple 2, 1. And the thing to think about for these is like, you know, Cartesian coordinates. So if you got xy coordinates in a plane, right, this first number is the x coordinate, this is the y coordinate. And you know, this is a different point from that point. Alright, so what we want to define is the Cartesian product. Which we write as A times B of 2 sets AB equals, and this is another set, but it's a set of tuples, a set of all tuples A comma B, such that A comes from A and B comes from B. Alright, let me give you an example, because examples work better. let A be the set 1, 2. Let B be the set R, S, T. So A cross B, the Cartesian product, is a set of tuples. It's the tuples where the first element comes from A and the second element comes from B. And it's all possible tuples like that. So for example, 1 comma R, 2 comma R, sorry, these are tuples, 1 comma S, 2 comma S, 1 comma T, 2 comma T. So that's the Cartesian product of A and B. And it's not commutative. If I take the Cartesian product of B with A, I get a set of tuples where the first element of the tuple comes from B and the second element comes from A. And since R comma 1 is not the same as 1 comma R, this element is contained in here but not here. These sets are not equal. So Cartesian products are generally not commutative. A cross B is not the same as B cross A. And the last thing worth note, again, if A and B are finite, the number of things in the cross product is the same as the number of things in A times the number of things in B. And you can convince yourself of that. Alright, so that's all I want to do for today. That's a bunch of stuff to chew on, but Wednesday I want to start talking about ways that we can combine sets. This is one way to combine sets. I want to look at other ways to combine sets, set operations, unions, intersections, complements, things like that. This is going to take us back to some Engineering 250 stuff. We'll tie this into functions and definitions of functions. We'll take a look at the homework that'll be due a week from Wednesday, and then we'll talk about some weird stuff related to sets. So we'll get into some interesting discussions. All right, that's all I got for today. I'll post this lecture later on this afternoon. Have a good one, and I will see you next time.
See you later.
All right, bye.
Take care, Nick.
Take
Thank
care.
you.